So this is where we left off. On Friday, we were talking about comb filtering, and I had let you listen to it, and hopefully you sort of understand what's happening there. So now we're going to find out if you understand what's happening there. So knowing what I've explained to you about phase and its relationship to frequency and wavelength, here's a question you should be able to figure out in your head. What delay applied to one of two 250 hertz sine waves would make it 90 degrees out of phase with the other? Right? So I got two sounds here. They are two sine waves, and they are both 250 hertz. And I would like to delay one of them so that it is 90 degrees out of phase. How much delay might I need to do that? Anybody care to take a crack at that? Okay, Deanne's close. So you know that 90 degrees represents a quarter of the wavelength, right? Offset. So if we just take, let's find out what the wavelength is of 250 hertz, right? So this should be 1,000 feet per second divided by 250 equals 4 feet, yes? Okay. So if 90 degrees out of phase would be a quarter of that wavelength, we can divide that by 4 and get 1 foot, right? And how long does it take sound to travel 1 foot? Yeah, 1 millisecond. Okay. So if I delayed that 250 hertz sine wave by 1 millisecond, it would now be 90 degrees out of phase with its twin. Make sense? Yeah? Okay. So let's test the extent to which this makes sense. Same scenario, but now I want to make it 270 degrees out of phase. Why would it be 3 milliseconds? Yeah, so if you chop a 360 degree wave up into chunks, right? 90 degrees would be a quarter of the wavelength. 180 degrees would be half the wavelength. 270 degrees would be 3/4 of the wavelength. And we already know that it takes us 1 millisecond to shift the phase 90 degrees. So if we want to do 180 degrees on top of that, that would be 3 milliseconds.
I know this isn't the point, but if you were just to do 90 degrees, wouldn't it be the same thing? Like going, if you put one back 90 degrees, wouldn't it be the same as going forward 270?
Yeah, but you can't take away time. You can only add time. Like, just we don't have the technology to remove time. But we can add time to our signals. But sure. Let's assume that technology existed, then yes, you'd be right.
I'm having trouble understanding this as well. So is it the same sound as it being 90, but just
Yeah,
time?
we can't hear phase. Right? So we can't hear that. It doesn't, whether it starts at 0 degrees or 90 degrees or 120 degrees, it doesn't matter. It sounds the same to us. So this is just about creating phase differences. We're just trying to I'm just trying to drive home the connection between phase and time and wavelength. Okay. Okay. So that aside, now let's learn how to do it with a calculator. So anybody ever taken computer science? No. Okay, well then this isn't going to look too, if you had, this would look familiar to you. Because I had my computer scientist friend help me write this out. And so, of course, she wrote it out like it's a computer algorithm. But it makes sense. So the idea here is how can we figure out what that frequency response would be of a signal that's getting comb filtered. And all I really care about is I just want to know which frequencies get canceled out and which frequencies get reinforced. And I know that the ones in between are going to be somewhere in between. I know that. So which ones are going to go away? Which ones are going to get louder? So this is how you figure that out. So F stands for the frequency. And the I is just some sort of integer value that we're going to iterate. So this will be a loop. So we'll start with 0. So I is integers that are greater and equal to 0. So we'll start with 0, and we'll just plug a 0 in for each of those. And so F0 just means the first frequency. Okay? And then I'd plug a 0 in for that I. And then T becomes the delay time in seconds in this case. So we're not going to do this one in milliseconds. We'll do it in seconds, because in this case, it makes the math a little bit easier. We can deal with less zeros if we do it in seconds. Okay. So we plug that in and we run that math, and we will get the frequency that gets canceled out. And then we put a number 1 in for I and run it again, and we'll get the next frequency that gets canceled out. Put a 2 in place for I, run it again, we'll get the next frequency that gets canceled out. We can keep doing that forever, and we'll keep getting frequencies that will get canceled out for that offset of time. And we can sort of adjust the formula a little bit, remove those 2's, and we'll get frequencies that get reinforced. So same process. You put a 0 in for I, and you do 0 plus 1 divided by the delay time in seconds, and you'll get the first frequency that gets reinforced. And you put a 1 in for I, and you'll get the next frequency that gets reinforced, so on and so forth. Okay?
So the I is just, so if you put a 4 in, that would just mean that this is the 4th frequency to get, that's
Yeah.
all that I means.
Technically the 5th, since you start with 0.
So
But
0 is the
yeah.
first one we put in.
Yeah. Yep. Okay, so we're going to try it. This will make more sense as we do it. So here's the scenario. You got 2 equal signals, arrive at a listener 1.5 milliseconds apart. What are the first 3 cancellations and reinforcements? So there are a couple of scenarios where this could happen. Maybe you've got 2 loudspeakers pointed at them, and one of them is 1.5 feet further away. There could be a reflection off of a wall that's coming to this listener 1.5 milliseconds later. There could be a lot of reasons why they would hear this, but what would it sound like in this situation? So what I want to do is we'll start just mapping it out over here. So I'm going to say 0 for cancellation, 0 for reinforcement, 1 for cancellation, 1 for reinforcement. I'm just going to kind of, because I want the first 3, right? 2 for cancellation and 2 for reinforcement. So I'm just going to create myself a little map here so I know which ones I'm doing. And these numbers are going to be the things I plug in for I. Okay, so the cancellation, I'm going to use this first formula. So that's going to be 2 times 0 in this case, right? Because 0, I'm putting in 0 for I, plus 1. Yeah? And then all of that is going to get divided by 2 times t. And what's t in this scenario? 1.5. Okay, but it's, well, we got to convert that to seconds, though, remember? Yeah, it'd be 0.0015 seconds, okay? Somebody want to run that math? So the way I would do this is I would first do the 2 times 0.0015. I get that number. And then I do this one. This will be basically 2 times 0 is 0, so you'd have 1. 1 divided by 2 times 0.0015, and you'll get some sort of answer. Anybody take a crack at that? Give me a number here.
333
That's what I got. So there's 2. Anybody else get that? Do I need to do it on my calculator? So let's see here. So on my calculator, so if I do 2 times 0.0015, right? Those were the numbers. I get 0.003. Yeah? So here's what I'm going to do. This is how this is in pCalc. Your calculator may want a different. I like to use the memory. pCalc has a little memory. So I'll say I'm going to put that number in memory so I can remember it. And then I'll go back to the top part of that equation, and it was 2 times 0 plus 1, right? So I know I don't have to do the calculator. I know 2 times 0 is 0. So all I'm really looking for end up with is 1. So I'm just going to do 1 is what I end up with. And I'm going to divide that by, and then I'm going to get this number back that was in memory. So memory recall. And then I hit enter, and I get 333.33 hertz.
I was putting 0.00115.
Oh, okay, yeah.
But, okay, now I get it. That's what I get.
Okay. So, oh no, did I lose my writing? I think I did. Bummer. Okay. So, first cancellation is 333.33 hertz. Did everyone end up getting that? Okay. So let's try, that's the first frequency that's going to get canceled out in this scenario. So the first reinforcement is going to be 0 plus 1 divided by t, and t is 0.0015. So this will be essentially 1 divided by 0.0015. Anybody want to take a crack at that one?
666.66 hertz.
That's what I got. It'd technically be 0.67. But yes, that's what I got. Anyone else get that?
I got that.
Must be right then. 3 of us got it. That's the first frequency that gets reinforced after that first cancellation. All right, so now let's look for the second cancellation. So that's going to be 2 times I, which is 1, right, in this case, plus 1, divided by 2 times 0.0015. So we already know that the 2 times 0.015 is 0.03, right? Or 0.003.
Yes.
Right? So we know that already. So in reality, I could just say, because we'll use that. I need to make my little eraser bigger. So 2 times 1 is 2, plus 1 is 3. So what's 3 divided by 0.003? Yes, 1,000 hertz. There's your 1,000, Dan. So let's try the first or the second reinforcement. Come on, pen. There we go. So that's going to be 1 plus 1 divided by 0.0015. Sorry, basically 2 divided by 0.0015. That's what I got. 333.3. I got 0.34.
Mine keeps going to 3. Yeah,
Going to 3?
You're adding 333.33 to
Yes, you'll see a pattern, right, as we start going through this. Once you figure out the first 2, you'll see the pattern, and you could really kind of sort it out from there. But let's practice doing the math anyway, just because it's important. So the third cancellation is going to be 2 times 2 plus 1 divided by, again, 0.003.
1,666.67.
Yep, the pattern holds up. And finally, our second reinforcement. That's going to be 2 plus 1 divided by 0.0015. Should be 2,000, yeah? Otherwise known as 2 kilohertz. You could write it as 2 kilohertz if you wanted to. Okay, make sense? It's not so bad. Looked really scary when I first showed it to you, and now you realize it's not so bad. In fact, once you do the first couple, you should be able to see a pattern, and that pattern should hold up all the way through on forever. Keep adding whatever that amount is, and it should be right. All right. Let's see. Here's another one. 2 loudspeakers, one 3 feet upstage of the other. Will comb filter with the first 4 cancellations? So I just want to know cancellations this time. So there is 3 feet of difference between these things. And I need to do that in time. So what would be the difference in time there? I need to figure that out first so I know what t equals. Remember that magic number 1.13? What do I do with that? Remember I said when you're going from feet to milliseconds and milliseconds to feet, you use a magic number, 1.13? Sort of. You're going to take 3 and divide it by 1.13. Because time is always a smaller number than distance. So if you already have distance and you want time, you're going to divide by 1.13 because that'll give you a smaller number, right? So 3 divided by 1.13 gets you, that's what I got, 2.65 milliseconds. What would that be in seconds? Yeah. Okay, there you go. So my first cancellation, so 0 for cancellation, would be 2 times 0 plus 1 divided by 2 times 0.00265. Anybody want to try to tackle that?
What's
Yeah.
the function of dividing by 1.13?
Well, so sound travels 1,130 feet per millisecond, or per 1,130 feet per second, which means it's 1.13 feet per millisecond. So 1.13 is this magic number that correlates feet to milliseconds.
You're just converting.
That's it. So that's just a magic number you should remember, that if you've got feet, divide it by 1.13 and you'll get milliseconds. If you have milliseconds, multiply it by 1.13 and you'll get feet.
Got 188.679.
Yeah, I rounded it to 6.8, but yes, that's what I got too. Anybody else get that? I need one more. You got it, John? Yeah. Okay, good. It must be right then. Usually. Just to keep things clean. Okay, so for the second cancellation, which would be 1 for I get 2 times 1 plus 1 divided by 0.00265. Anybody want to try that one?
566.0378.
Yeah, I did 0.4, but yes, that's what I got. Anybody else get that? Dan, did you get that? Okay. Make sure. Need one more to concur. Yes? Must be right. Yeah? Okay, good. All right, next one would be 2 for I. So that's going to be 2 times 2 plus 1 divided by 2 times 0.00265.
943.
Yep, that's what I got. Anybody else get that? Yes? Excellent. Doing all right. Well, it gets really scary when everyone got a different answer. And then I think, oh man, am I wrong or are they wrong or who's right? I never know. All right, this one would be 2 times 3 plus 1 divided by 2 times 0.00265. I don't know. I got 1132.08. Am I wrong?
I got 132.
Yeah, that's what I got too.
Again,
I got 132
Because it's 7 divided by 0.0053.
yep, and I got 1,320.75.
So off by 1 from you.
They're off by 200 grams.
Let's see. Let me save this real quick. Capture. Ah, sorry about that. Okay, so 2 times 0.00265 times 2. Is that right?
Why did you multiply by 2 twice?
Because my thing is laggy. All right, 2 times 0.00265. There we go. That's right. Let's put that in there. And then I did 2 times 3 plus 1, 7 divided by, recall, yep, 13275. You were right, my notes are wrong. Excellent. See, this is why we need more 3 people. Because sometimes I'm wrong. I miscalculated somewhere in there. All right, so that would be, what's the new number again?
1,320.
There you go. Yay, we did it. Oops. Okay, so, stop. Clear. Okay, there we go. All right, so here's a little curveball I'll throw at you now. So what if we did this backwards? Because why not? So the question is, it's already comb filtering, and I don't know why. But I can see when I measure the signal that I've got a first reinforcement at 1.5 kilohertz. In that scenario where the first reinforcement is 1.5 kilohertz, what would the first cancellation be? Well, ultimately I'm looking for this answer, right? First cancellation. So in order to do that, I've got to figure out what offset in time we're talking about in this scenario. Because I can't find a cancellation unless I know time. I got to have a value for t. So if I reverse engineer my formula here for reinforcement to solve for t, and again, my mathematician friends assure me that this is the version of that formula that solves for t. Yes? Okay. Someday I'll tell you the story about how I cheated the system and never quite finished Algebra 2, but managed to graduate high school anyway. Um, so I don't think I could get away with that today, but I exploited a loophole. All right, so that's solving for t. So I should be able to figure it out now. So if t equals I plus 1 divided by the frequency index, then that is going to look like t equals 0 plus 1, right? Because first cancellation would be 0 for I, divided by frequency I, and the frequency is that, 1500 hertz. So what's 1 divided by 1500? That's what it breaks down to.
0.06 repeating.
Seconds, right? There you go. We got t. So now the first cancellation would be 0 for I. 0 cancellation to be 2 times 0 plus 1. All of that divided by 2 times 0.00067. What'd you get? I didn't get.
Really wrong.
I didn't get that either.
I got 769.
I got 746.27.
Okay, so
It's 1 divided by 0.00.
shouldn't that not be
Yeah. So this is 2 times this is 0.00134, right?
half of 1.5?
So 1 divided by 0.00134.
2 times 1 divided by 0.00134.
You got that now?
Yeah.
Okay. So I'm right?
Yeah.
Okay, I'm right.
Definitely
Okay.
put in 3 instead of 1.
Okay. All right. Good. Oh, right. Order of operations, right? You forget to. Yes. Okay. I got you.
Well, no, I was just calculating the second reinforcement, not the first.
Oh, I see. All right.
So I had 3 times that.
All right. There you go. So we got it. Everyone got this now? Okay. That's hertz, by the way. Excellent. Okay. So there we go. I think I got. This is same kind of problem, just now I know the first cancellation, so I'm trying to save some time because we were supposed to do this on Friday, so I'm not going to do all of these in class, but I do want to just highlight this, which is the cancellation formula solved for t. You may want to jot that down in case, so you don't have to figure it out yourself later, because I will have a couple of these questions on the homework, and we will review those on Friday. So just jot that down. Yes?
Not due today.
No. Friday.
Oh,
I
did a lot of it.
did all of it.
we did all that we could.
Yeah. Syllabus says Friday, right?
I just assumed it was today.
Yeah.
So I did it.
Okay. Friday.
Let's check that out. We were all just like, oh, crap.
So jot that formula down, and then you'll need that for there should be a question on the homework that's like this. But same process, solve for t using 640 hertz. Once you have your delay time, then you can use that to convert it to feet, right? Because you'll get seconds, convert that to feet, and you'll have your distance. How far do you have to offset it?
So the first one we did was solving for t using the reinforcement.
Yeah. Mm-hmm. And ultimately, you don't have to then do it front ways again. You're just going to do the whole thing backwards because all you really want to know is t. Then convert t back to distance, which you just multiply by 1.13 after you've put it into milliseconds, and you'll be all set. Okay? This one, you should do this on your own. I think this very one is on the homework. Two singers in a musical standing 6 inches apart, but they're both wearing microphones. They're going to comb filter, okay? Because they're both mics are going to pick up both voices, and then you're going to mix them together, but they'll be at different times, and so they're going to comb filter in the board before they even go out to the loudspeakers, so that everyone in the audience hears that, okay? Bane of my existence. Just for the, you can, so you would convert 6 inches into feet, convert that into milliseconds, convert milliseconds into, to seconds, and then you got t. And then you can figure that out. So just to skip ahead here, it works out to this way. So cancellations would be 1.13 kilohertz. You'll get another cancellation at 500 or 5.65 kilohertz. You'll get another one. Oh, wait, sorry. That's the second one. Another one would be 3.39 kilohertz, so on and so forth. So it obliterates that range, that 1 to 4K range, that is so critical for us, which is why every time you get to the part of the musical where there's the love song and the director or choreographer choreographs them to stare lovingly in each other's eyes from 6 inches away and sing the most beautiful song of the whole show, that's why we die a little inside, because that scenario obliterates the frequency spectrum that is most important to us. Okay? So you can work on that, hopefully on your own. Okay, good. Now we can get to the next little bit. So I've shown you everything you need to know to do the comb filtering math and the homework now. And those are just some more practice ones. Yes?
The last two questions on the homework that have to do with Friedman and Catawba.
Uh-huh.
How do we do those? We don't have those numbers.
You would have to pull up a CAD file. And you would have to measure that CAD file, I would imagine.
What I heard was break into Friedman with a tape measure.
Yes. That's what I used to make people do. But you can't get in there now. So, yeah, you can pull up a CAD file. You can measure it. If you don't know how to do that, I can show you, or one of your buddies can show you.
He might actually correct. I don't know how correct it is though.
Well, I know it's on the server. I don't know where on the server. It's always
DP it's that DP server. You log in there.
Production assignments. It has the CAD files for the last 10 years or something.
Is it not on?
It doesn't matter if they're perfectly accurate.
Wallace
It's working with the
or
same set of
Eggman?
numbers.
What's that?
It's not on
Should be on
our servers.
It might be somewhere if you dig around.
How do you get to it if it's not? How do you get? We can do this after.
Yeah.
But do you have questions?
All right. Another concept I want to drive home here before I get into my little toys is this concept of diffraction. Diffraction is what happens when sound is blocked or attempts to be blocked by some sort of object. So remember I said you can't dodge sound. You can't duck and have it miss you. It'll get you every time. But you can put something in the way. So you could hide behind something, and maybe you might be able to avoid it. And the effectiveness of that strategy is going to depend on how large the object is compared to how large the sound is that you're trying to block. The important thing to remember about this is sound sees obstructions differently than we do. So, if you were to look at the back of this chair, this little material here on the back of this chair, if you were to try to describe this to me in the simplest way, using the fewest words possible, how could you describe what this material on the back of this chair looks like? Mesh. And what is mesh? What do you mean by mesh? What? Yeah. Holes. Who said that? Yes, holes. It's a bunch of holes, right? There's a whole lot of holes in the back of this thing. Okay? That's what human beings tend to look at something like this, and we see the holes first. And then later we sort of realize that there's more going on here than just holes. Okay? Here's the important thing about sound, is sound does not see holes. Sound sees obstructions. And so sound would look at the back of this chair and say, that's a whole lot of little obstructions. So sound is going to see the little stitching between the holes. And that's what it cares about. Because the size of the obstruction compared to the size of the wavelength of the sound is going to have an impact on how effective that obstruction is going to be at blocking the sound. So if the object or the obstacle is very large relative to the wavelength of the frequency that you're trying to block, then it will have some amount of effectiveness in blocking that sound. Eventually, the sound will get around it because energy, doesn't go away. So it'll push on that object enough, and eventually that energy will just kind of wrap around that object. So that's the diffraction part. So it ends up kind of the path that it was traveling is diffracted. You do have a little area right behind that obstruction that's the shaded area, we call it, where the sound will be significantly quieter, maybe non-existent. If you ever drive on the freeway, you'll notice there's usually big walls, on the interstates. And that's what this is trying to do, is they're trying to make, they can't block all of that sound of all the cars, but what they can do is if the car is here, driving down the street, making all of this sound, and then your house is here. If this wall is tall enough, then the sound from that freeway will diffract over that wall, but you'll be in that shadow area where it's not quite so loud. And then this house here, eventually that sound is going to get to them, but it'll be a lot quieter at that point because sound gets quieter the longer it travels. Okay, so that's the idea here. Is you're trying to kind of block. You're trying to create that little shadow right there. That only happens if the obstacle is larger than the wavelength of the frequency you're trying to block. Yeah.
So, just trying to kind of understand the concept. So, if you're listening to music very loudly, and you walk upstairs, and it's all when you get upstairs, you can still hear it, but it's much more. It's mostly just the lower frequency.
Yeah.
Is that resonant frequency, or is that diffraction?
Yeah, it's diffraction because the high frequencies, it's easier to block them, right? Because they have smaller wavelengths, right? Whereas, the low frequencies, 100 hertz is like 11 feet long, so, your walls are not that tall. Yeah. You don't have 11-foot tall walls. So those low frequencies tend to get around because if the object is smaller than the wavelength, then it goes around it as though it didn't exist. So that's what's happening over here is this area behind this smaller obstruction, there's no diffraction happening there. There's no shaded area where the sound is quieter because we call that acoustically transparent. So obstacles that are smaller than the wavelengths of the frequencies that you're caring about, those objects are transparent. Yeah?
So technically walking or being across that room behind that door is diffraction in a way.
Well, the diffraction is just what happens to the wave, right? The wave kind of shifts, right? But the phenomenon is it's about are you blocking the sound or are you not blocking the sound, okay? And that's the take-home message here, is understanding that if you want to block the sound, you need a really big obstacle, especially if you want to block the low frequencies. So sometimes we try to keep sound from going places, right? It's like, oh, I don't want the sound to be in that room next door. Well, one of the first things you're going to have to do is get a really, really, really large obstacle to stop all of that sound. That's the first thing you have to do. Then a whole bunch of other variables come into play. Yeah?
Does that have to do with two things? Okay, first off, earplugs. The first thing they do is cut down higher frequencies. Just like the cheap ones are just taking away all
Yeah.
the highest stuff. Is that because of this?
Mm-hmm.
And then, is that the reason different thickness of acoustic paneling and having different like ones that were like, I don't remember what you called it, or like one panel has 15 different thicknesses.
Yeah,
Does that have to
that's
do
a
with
different
something
thing.
else?
That's different, but similar concept in that if you in this so this does apply to like absorption panels and diffusion panels and things like this, is that if you want to affect that sound in some way, whether it's absorb it or reflect it in a certain way or block it in a certain way, whatever object you use to impact that sound has to be bigger than the sound. It has to be physically larger than that sound. And we know now how to figure out how large the sound waves are. We can figure out their wavelengths, right? But even more important, and where you will encounter this phenomenon more often, is when you have to get your sound to go through an obstacle. In theater, in particular, they really don't like to see loudspeakers for some reason. People really don't like to see loudspeakers. I don't know why. Quite happy to look at lights. But for some reason, looking at loudspeakers is just thoroughly offensive to a lot of people. I don't know, and I haven't yet to figure that out. And so you're always being asked to like hide your loudspeakers behind things, okay, and still get the sound out. So the important thing, if you're trying to make sure the sound gets out, is not about poking holes in it. It's about making the obstructions as small as possible. So it's not about how many holes you have. So let's say you have to hide your loudspeaker behind a wall, and you want to get the sound to come through it. Okay, yes, some holes will help, but it's not about how many holes you have, or it's not even about how large the holes are. It's about how large the space between the holes is. So how big is that space between the holes? If it's 4 inches, then frequencies that have a wavelength of 4 inches or less are not going to get through that very efficiently. So it's more about the space between the holes that matters. You could do really large holes or really small holes. It doesn't really matter. What matters is how far apart are they.
I told Richard that we'd be millionaires if we made speakers that look like Source 4s.
Yeah, probably. Yeah. So that's just an important concept to understand. The other is I want to talk about the effects of wind and temperature. I kind of alluded to that early on last week, that wind and temperature and humidity and things like that do affect the speed of sound. So let's talk about temperature first. So sound travels faster in warmer temperatures. Okay? So the higher the temperature, the faster the speed of sound. And conversely, the lower the temperature, the slower sound travels. Okay? But you might, and probably will, at some point in your career, maybe more than once, find yourself in a situation where the temperature of the air is not consistent. This happens certainly outdoors. If you ever do shows outside, you'll tend to set everything up during the day when the sun's out, and then you do the show at night, right? Usually just as it starts getting dark, because that's when the lights start being useful. And so just as the sun is going down, you end up in this really bizarre situation where the ground is still warm because the sun's been beaten down on it all day. But the air above it starts cooling off because the sun's not there. And you get this odd temperature gradient. So it's warm down on the ground and it's cool up in the air. And then you've got, here's your stage, and here's your performer, and you've got a loudspeaker here. So, and it's sort of traveling through here. Well, what happens is, your sound is coming out here like this, and the air part of this that is down towards the ground is going to move faster than the part of it that's up here. So it ends up kind of looking like this. So down here towards the ground, it's moving really fast, and up in the air, it's moving really slow. And the effect of that is it seems as though the sound is drifting up. So everything sounded great in sound check when the sun was out, and then the sun goes down, you start the show, and everything gets a lot quieter. And it's because of this, because you have this weird temperature gradient that is diffracting, again, that propagation of that sound, which is really frustrating. I've seen and heard this happen in theaters indoors as well, really large theaters. You have to have a little bit of space before this really kicks in. But in really large theaters, this can happen, because usually the air conditioning is up in the air, right, up in the ceiling. And you tech the show without the audience there. And you've got this air conditioner that's designed to cool 2,000 people. And there's 10 people in the room during tech. And so that's why it's always cold in tech. That's why everyone's always freezing during a tech rehearsal, because you've got an air conditioner that's designed to cool 2,000 people, and there's 10 people in the room. Okay, so those 10 people are cold. Okay, so you tech show, great, everything's awesome, you get all your levels set, everything sounds good. And you're operating in this cold room where sound moves slower, okay? And then the first preview or opening night, you suddenly fill it full of 2,000 people. And people are just enormous hot water bottles, right? That's what we are. We are big bags of hot water, 98.7 degrees, okay? So what happens is down there on the floor, it suddenly gets really hot, because you got 2,000 enormous hot water bottles sitting down there on the ground, and now you got your air conditioner up in the air kicking in, trying to cool down those 2,000 hot water bottles. You create a very similar temperature gradient. Cold air up above, really hot air down to the seats, same thing. Sound goes up to the sky, okay? And you'll freak out. And they'll think, oh crap, everything's quieter. I got to change the whole show. I'm going to reprogram the whole show right now because everything's going to be quieter. But hold off a little bit. If you'll wait a little bit, usually that gradient will even out a little bit, because suddenly that air conditioner will start cooling off all those hot people, and it won't be as big of a deal. It's going to sound really weird for the first 20 minutes of the show, and then eventually it's going to even out a little bit. Again, this happens mostly in really large theaters. Small theaters, not so much, just because it takes some space for this phenomenon to really kind of do its thing. But it definitely happened. Now, certainly, people absorb the sound more, and so that has some effect on how loud things are perceived. But temperature certainly plays a part. Yeah.
So, if the cold air is above the people, like above where you're listening, why does it affect the volume if you can't tell? Because you're still getting hit in the warm air, which means that it should be.
Yeah. Well, it's just what I'm saying is that the field where the sound is propagating, that sound is not being able to propagate at the same speed at all altitudes. Okay. So down below, it's moving faster. And that has the effect of it seeming as though essentially all that energy gets stuck up above, because it's being slowed down up there, but it's moving really quickly down at the floor. And so, yes, you're hearing it, but before, when you were teching the show, it was cold down there. And so all the sound was getting stuck down on the ground. And so that energy was building up, and it sounded louder. And now that's not happening anymore, because all that sound is trying to run away from that hot air. Okay? So I'm not saying that it goes silent. Yeah, you still hear plenty. It just sounds a little quieter. And you're going to wonder why. By the way, if you flip that scenario, if you try to do a show in the morning outside, and it's cold on the ground and warm up in the air, then you get the opposite thing. The sound seems to dump down towards the ground, and it kind of trips over itself, right? So it hits the ground, it gets built up in there, and then bounces off, and then does the same thing again, and it keeps bouncing off the floor and just like hops all over. So your perception of sound level down on the ground is going to be really erratic. You could move from front row to back row, and it's going to change dramatically row to row, because the sound is just kind of going Okay, it's just kind of tripping over itself. Okay,
Solve that.
you can't. That's my point. Is you can't do anything about it. So don't.
Rearrange your speakers to make that happen less.
It's a moving target.
You'd have to change them for every degree that air.
Yeah, it's like, as you go through the night, on the scenario above, that ground's going to get cooler and cooler and cooler. So you can't do anything about it. So I'm not telling you this because there's a solution to it. There's not. I'm just telling you so you don't freak out when it happens. Okay. Air does something similar. So, if you're trying to hit your sound up against a breeze coming at you, then your sound is going to tend to drift up because it's pushing against this air that's coming at it. And remember, sound is air. And so the air flow is opposing the propagation of your sound. That's going to have the effect of the energy going up. Whereas if you have, I really should have my loudspeaker here. So if you have the sound or the air going this way, it's going to have the effect of pushing your sound down towards the ground. Okay? So that is, if you've got a consistent breeze, like if you've ever done like a show at the beach, okay, and the ocean is over here, and there's usually wind coming this way, you can sometimes tip your loudspeakers up a little bit because you almost always have wind coming at you off of the ocean. You can tip your loudspeakers up just a little bit, and then the wind will catch it and dump it down to the seats. All right.
Please start doing shows at the beach.
We used to. We have a whole lot of weather-treated loudspeakers, and that's why we used to do a show out on the Outer Banks every summer.
Isn't that why a bunch of them are labeled a certain way?
Yeah, the Manteo is a city out on the Outer Banks. We used to do a show out there. Okay, I think that's it. Okay, great. So I've covered all of I got. Yeah.
For all of these, how dramatic is this effect?
It depends.
Like,
It depends.
so
Sometimes not very dramatic, sometimes really dramatic.
something that, like, if it's bad, it could completely
Yeah, it could really mess you up.
show
But
really bad.
again, you can't do anything about it, right? You can't control the temperature or the atmosphere or the grade. You can't do anything about that. You don't have tools to fix that. But you just need to be aware that these things do affect your sound. And so don't overreact. You don't want to go and reprogram the entire show at intermission just because Act 1 sounded funny. Because by the time Act 2 comes, the temperature is going to change again, and it'll sound different in a different way. You know how to fix it. It's just sort of stay the course, All right. So I've got a couple of, I think we got time here, it looks like. So I've got a couple of little gizmos I'm going to show you. And these are not going to be particularly meaningful in the video. So I'm going to go ahead and stop the video.